So welcome to the sixth lecture of module 6. So in lecture number 5 we have seen two types of strain gauges, that is bonded strain gauge and unbonded strain gauge. And what is the advantage of that unbonded strain gauge have when compared to bonded strain gauge? See, first one is that it doesn't have any creep. So what is creep? So creep is nothing but, see, in bonded strain gauge we have an intermediately layer called a backing which is made of epoxy resin or paper. So this is a material which first collects the strain from the specimen. So whatever strain is collected from the specimen by the backing is actually given to or passed on to the wires, strain wires. So what we see is that the strain wires are strained much less than the strain of the specimen because we have an intermediary layer or a backing to take up that strain. So that less strain is actually called creep. So that creep is indefinitely there and invariably there in a bonded strain gauge. Now we don't have such a problem in unbonded strain gauge because we have the strain wires directly attached to the specimen. So, and another, that is one advantage. Then as there is the absence of the backing layer in unbonded one, hysteresis is also less. The lag is also less. Now the next advantage is that unlike a bonded strain gauge, the unbonded strain gauge is less crowded. The structure, the layers are less crowded, so that helps in better heat dissipation, or that helps in a better thermal stability. So these are all the advantages that the unbonded strain gauge has when we compare with the bonded strain gauge. Now the next type is foil strain gauge, which is more or less regularly used strain gauge. That is, instead of wires we have foils, aluminum foils, which are again attached to a backing which has a base. So this is the point, this is the axis where we apply the force. So we can definitely see that we have more surface area. So surface area, if it is more strain is picked up by the gauge. That is important. That reduces the creep. And you can see that the cross strips are less in length and much thicker, and this avoids cross sensitivity, or this reduces the influence of cross sensitivity. So this helps in pickup of more strain, and as surface area is larger, it helps in more heat dissipation, which helps in increased thermal stability. So these are the advantages that foil strain gauges have when compared to wire strain gauges. And there is another class of electrical strain gauge also, that is semiconductor strain gauge, which is out of the scope of my lecture here. You can read from the literature. So now we'll move on to a little bit of mathematics. That is, we'll go to the how that strain is converted to voltage. Now there are two ways by which we can convert. One is use the potentiometer circuit. We know why the potentiometer is used. Potentiometer can be used to measure the voltage. One is that, and that is again out of the scope of the video. And today in this lecture we'll see how we use Wheatstone's bridge to convert strain to corresponding voltages. So we know what is Wheatstone's bridge. Wheatstone's bridge is regularly used to measure medium resistance, that is from 1 ohms to 100 ohms. So here you can see that there are four resistance arms. Four resistance arms carry 4 active strain gauges. So what is this voltage? This voltage is nothing but voltage between B and A minus voltage between D and A. So this is what EVA all about. That is the total voltage E multiplied by R1 by R1 plus R2. What is EDA? That is the total voltage E multiplied by R4 divided by R3 plus R4. After manipulation we'll get this one, where we see that if my R1 R3 is equal to R2 R4, then the numerator becomes 0 and E also becomes 0. That is the point that we can tell that the bridge is balanced. So what is the condition for balance? The condition for balance is that the product R1 R3 should be equal to R2 R4. Now suppose we have some strain. So when we have some strain, then each resistance will be enhanced by some resistance, that is R1 will be increased by delta R1, R2 by delta R2, R3 by delta R3, and R4 by delta R4. So if you do all those, make all the substitution, we'll get such an equation. Okay. Now we can make some valid approximation. That is, what is second order non-linearity terms? That is, if we have 0.5, suppose if we find the 0.5 square, we'll get 0.25. That is even smaller term. So when we open up all the brackets, we'll multiply one delta term with another delta term. That is, delta R1 will be multiplied by delta R3. We find some 3 more terms like that. That is delta multiplied by another delta. So when we multiply a delta term multiplied by a delta term, that is an infinitesimally small term multiplied by another infinitesimally small term, we get an even smaller term. So we can neglect such terms. And we impose the initial condition. What is the initial balance condition? R1, R3 equal to R2, R4. We'll get an equation like this. So it involves some tedious mathematics. So you can do and see. And this term is very important. That is R1, R2 by R1 plus R2 the whole square is very important. We have to make a substitution here. That is why. So this term is again the same. And this term we have to make a substitution. So what is that substitution? So that substitution is that instead of that term, we have substituting a by 1 plus a the whole squared. So what is a? A is nothing but a is from the balance equation, initial balance equation, that is R1, R3 equal to R2, R4. So what is a? A is taken as R1 by R2. So how that is substituted here? So how this term is replaced, it has replaced R1, R2 by R1 plus R2 the whole square. That is, we'll go the reverse order. If it is a by 1 plus a the whole square, we know that a is R1 by R2. So if you substitute that here, this is what we get. Find the LCM, we get this one. Open up, cancel the terms of R2, we'll get R1, R2 by R1 plus R2 the whole square. This is the point where we started. So this value in that equation can be substituted by a by 1 plus a the whole square. Okay. And then, before going to the next step, we'll see one more thing. That is, suppose if we take a material of length L, and if we apply the force in this direction, obviously the length will be increased by delta L. So we know that initial resistance of the material as R is equal to rho L by A. So if you find the derivative of or the change in resistance with respect to stress, then there are 3 factors which get affected. One is rho, other is L, and that other is A. So we find everything. Instead of R, we substitute rho L by A. So we'll get that. First we'll see the partial derivative of L with respect to stress. Then we'll find the partial derivative of A with respect to stress. And then we'll find the partial derivative of resistivity with respect to stress. We'll get these 3 terms. And if you multiply the whole thing, the whole equation by, if you multiply the whole equation by 1 by R, and if you substitute instead of R as rho L by A, after cancellation we'll get 1 by L, after cancellation we'll get 1 by A, and after cancellation we'll get 1 by rho. So we'll see that delta R is a derivative of R, dr is nothing but delta R. So if you multiply the whole thing by, if we take this term to the other side, we can cancel dou sigma. All the terms of dou sigma gets cancelled. What is remaining in the LHS part will be dr by R, and what is remaining here is dou L by L. Here it is minus dou A by A, and here it is plus dou rho by rho. So this can be replaced as delta R. Dou L can be replaced by delta L. This is replaced by delta A, and this is replaced by delta rho. So everything remaining will be delta R by R is equal to delta L by L minus delta A by A plus delta rho by rho. So we can make one assumption that if the change in area is very small, then this can be replaced as 2 times delta D by D. So again, we know that as there is an increase longitudinally, there is a reduction in the transverse direction. So that can be shown by the Poisson's ratio as delta D by D as minus mu, that is Poisson's ratio multiplied by delta L by L. So if we substitute everything, that is instead of delta A by A, we substitute 2 dou by D, and instead of delta D by D, we substitute minus mu delta L by L, we'll get this term, that is 2 mu delta L by L. So everything is here, and if we divide the whole equation by delta L by L, we'll get 1 plus 2 nu plus this term. This whole term is nothing but the gauge factor. So this is very important, that is delta R by R divided by delta L by L is nothing but the gauge factor. Now we'll go to the last step, that is, so again I recall, that is delta R by R divided by delta L equal to the gauge factor G. So what is delta R by R? Delta R by R is nothing but the gauge factor multiplied by the strain, that is G multiplied by eta. So the last step is this value from the strain gauge 1 can be substituted as G1 eta 1, likewise Geta E2, G3 E3 eta 3, and G4 eta 4 multiplied by E and A by 1 plus A the whole square. So you can see that the generated EMF in the Wheatstone's bridge is the algebraic sum of the 4 strain values, algebraic addition of the 4 strain values in the bridge. So that is how we quantify the strain to the electrical voltage, and we know how to calibrate the strain to stress also. So that is why strain gauges are very important, and this equation is also very important. That is how the value of strain is quantified. Thank you for the patient listening.